In this video, we'll be looking at calculus with parametric curves. Suppose f and g are differentiable functions, and we want to find the tangent line at a point on the parametric curve. X equals f of t and y equals g of t. Y is a differentiable function of x. Then we use the chain rule to find dy dt. That is dy dx times dx dt. We could also write that this way. Dy dt is the derivative of y with respect to t divided by the derivative of x with respect to t, assuming that dx dt is not 0. We still can't divide by 0. And then later, we can also look at the second derivative. Remember, the second derivative deals with concavity. So in this example, we want to find an equation of the tangent line to the curve at the given point 0, 3. We'll start by finding the derivative dy dx. And remember, that is dy dt divided by dx dt. In the numerator, we're finding the derivative of y with respect to t. So that would give us 2t plus 1. In the denominator, we want to find the derivative of x with respect to t. That gives us 2t minus 1. So I'll just make a note that this is the first derivative. To find the t value corresponding to the point 0, 3, let's solve the equation x equals 0. So let's say that we want x, this point here, to be 0. So 0 equals t squared minus t. From here we can factor the quadratic. We'll factor out a t. Set each of those factors equal to 0. And we get t equals 0, and we get t equals 1. Now, only one of those will give us the corresponding y value of 3. If we plug in 0 for t up here for y, so y equals 0 squared plus 0 plus 1, that is not equal to 3. So we're not going to use a t value of 0. Let's see what happens when t is equal to 1. So only t equals 1 gives y equals 3. And let's just confirm that. Y equals 1 squared plus 1 plus 1, and that gives us 3. So again, x is 0, y is 3. That point 0, 3 happens when our t is 1. So with that information now, with t equals 1, let's find dy dx. Again, we're plugging 1 in for t in the equation for dy dx. We have 2 times 1 plus 1 divided by 2 times 1 minus 1. This gives us 3 divided by 1, which is 3. So remember what 3 tells us? That is the derivative. Remember, derivative is all about slope. So this is going to be the slope of the tangent line at the point 0, 3. So now the equation of the tangent line. We'll use y minus y1 equals m times x minus x1. Let's start with that point slope form and just plug in what we know now. We have 1 minus the y value is the initial y value of the point that we were given, 3. M is this 3, the slope. Don't confuse those two. And then we have x minus the initial x value, which we were told is 0. So let's put this in slope-intercept form. We get y equals 3x plus 3. And we now have the equation of the tangent line to the curve at the point 0, 3. In case you want a visual as to what that might look like, I've created this in Desmos. So here we'll sketch out the curve. The parametric curve is here. We have the point 0, 3 on the y-axis, and we're looking for the tangent line at that point. And there we have it. Y equals 3x plus 3 is the tangent at 0, 3. In this example, we're looking for concavity. And remember that to find concavity, we need the second derivative. That is d dt of dy dx divided by dx dt. So recall the first derivative from earlier. We want to take its derivative. To do that, we need the quotient rule. So we'll take 2t minus 1 and multiply it by 2 minus 2t plus 1 and multiply it by 2. All of that is divided by the denominator squared, 2t minus 1 squared. And in the denominator of the big fraction, we have dx dt. So that is 2t minus 1. Simplifying this, we get 4t minus 2 minus 4t minus 2 divided by 2t minus 1 squared, all divided by 2t minus 1. Simplifying a little more in the numerator, we'll get negative 4, and then we have a fraction divided by a fraction. Remember the rule, keep, change, flip. That's just going to push this into the upper denominator, giving us 2t minus 1 cubed. And now that we have the second derivative, we can test for concavity. When the second derivative is positive, we have concave up, and when it's negative, we have concave down. We'll first focus on concave up. To solve a rational inequality like this, remember you look at your x-intercepts and your vertical asymptotes. In this case, there's no x in the numerator, so there are no x-intercepts of this rational function, but we do have some vertical asymptotes. So let's look at setting that denominator equal to 0 and find the vertical asymptotes of the rational expression. We get t equals 1/2. And what we'll do is we'll put that on a number line and then look at values to the left and the right of 1/2. So if we think of 1, something on the right side of 1/2, for example 1, plug 1 into this function. Negative 4, 2 times 1 minus 1 cubed. We're asking, is that positive? We have negative 4 divided by 2 minus 1 is 1, 1 cubed is 1. We get negative 4 is greater than 0. That's a false statement. So we know that this side is not concave up. It's actually going to be concave down. And now let's test a value to the left of 1/2. Any value you want. I'm going to choose 0. It'll be relatively easy to test 0. So negative 4 divided by 2 times 0 minus 1 cubed. And again, we're asking, is that positive? We have negative 4 divided by 0 minus 1 cubed. Negative 1 cubed is negative 1. So we get negative 4 divided by negative 1, that's 4. 4 is indeed bigger than 0. So this one works. That one is concave up. So for concavity, it looks like we are concave up when t is less than a half, and concave down when t is greater than 1/2. Now we don't really have restrictions on t in this case, but sometimes we'll deal with only positive values of t. In that case, it would be from 0 to 1/2 for concave up. In this video, we will again be finding tangent lines to a parametric curve. Let's start by graphing the curve. In Desmos, I already have for you the two equations, and let's see what happens when we trace out t. So we get this cool looking shape, and we first want to find where the graph crosses itself. And it looks like it's happening at 1, 0. We will prove that first, and then once we verify that that is indeed the point where the graph crosses itself, we can find the tangent lines. Note that there will be two of them, one where the graph is concave up, and then again where the graph is concave down. So it appears to cross at 1, 0. Let's prove that fact. So if it's true, then x equals 1, we can plug that in to the first equation. 1 equals -2 cosine t. And let's solve this equation. We have -1/2 equals cosine of t. Now think about the unit circle. Where is cosine, the x value, -1/2? That happens when t is 2 pi thirds or when t is 4 pi thirds. And that is assuming that we are looking at values between 0 and 2 pi. Let's sub either of those into the other equation. So I'm just going to look at 2 pi thirds and focus on it for a moment. And we'll plug that into the y equation. Y equals sine of 2 pi thirds plus sine of 2 times 2 pi thirds. Going back to the unit circle, sine of 2 pi thirds. That will give us the square root of 3 over 2. Then we want to add the sine of 4 pi thirds. That is actually negative root 3 over 2. And so we get that y is 0. Does that satisfy the point? We made x 1, and the y value spit out a value of 0, 1, 0. So this satisfies the point 1, 0. So we confirmed that that is indeed where the two graphs cross. It looked like it. We've proved it now. Let's next find dy dx. Remember, to do that, we take the derivative of y with respect to t and divide that by the derivative of x with respect to t. So dy dt. Up here, we have the derivative is cosine t plus 2 times cosine of 2t divided by dx dt. So now we're focusing on x. Derivative there is 2 sine t. So I'll just make note, this is my derivative. Next, let's see what happens when t is equal to 2 pi thirds. So now dy dx at the value 2 pi thirds. We're just going to plug that in for t. We have cosine 2 pi thirds plus 2 cosine of 2 times 2 pi thirds divided by 2 sine of 2 pi thirds. Lots of practice with the unit circle here. So cosine of 2 pi thirds, that is negative 1/2, plus 2 times cosine of 4 pi thirds. That would give us negative 1/2, all divided by 2 times the sine of 2 pi thirds. That is root 3 divided by 2. Continuing to simplify that, we now have, let's see, that is negative 3/2 divided by root 3. That will give us negative 3 over 2 root 3. And let's go ahead and rationalize that denominator. We now get negative 3 root 3 divided by 2 times 3. 3's will reduce, leaving us with negative root 3 over 2. So this is the derivative when t is equal to 2 pi thirds. Keep in mind that is the slope of the tangent line when t is, again, 2 pi thirds. So let's find the tangent line. Y minus 0 equals the slope we just found, negative root 3 over 2, times x minus 1. This is the equation of the tangent line, again, at the point 1, 0. But there were two of them. Let's try to find the other. The other t value was when t was 4 pi thirds. We need to find the value of the derivative at 4 pi thirds. So dy dx. We have cosine of 4 pi thirds plus 2 cosine of 2 times 4 pi thirds divided by 2 sine of 4 pi thirds. Again, lots of unit circle practice. We have negative 1/2 plus 2 times the cosine of 8 pi thirds. That is negative 1/2 divided by 2 sine of 4 pi thirds, negative root 3 over 2. Continuing to simplify, we get negative 3/2 divided by this negative root 3. That is 3 divided by 2 root 3. Let's again rationalize that denominator just to make it look a little prettier. We get 3 root 3 over 2 times 3. The 3's reduced, leaving us with positive root 3 over 2. Again, this is the slope of the tangent line. So our next tangent line, we have y minus 0 equals the slope we just found times x minus 1. Simplifying this, we get y equals the square root of 3 divided by 2x minus square root of 3 over 2. This is, again, the equation of the tangent line at 1, 0. Now that we found them, let's add those to the graph from earlier and see if they look accurate. Going back to the previous graph, let's type in those equations, see if they look correct. That first one looks pretty good. Notice it's going through 1, and it does look like it's tangent to the curve at that point. The next one, we just change some signs around, and it looks good as well. So there we have it. Looks like the visual proves that we have our two tangent lines.